Good afternoon, everyone. This is our lecture 3. So today I want to make a few announcements regarding the homework and the study groups or your final project group formation. And to assist you to connect with each other, I would leave the Zoom open after the lecture ends. So I will maybe randomly assign one of you who stays as the co-host, as the host, then I'll leave the Zoom room. So for those of you who are interested in having a discussion with each other, you can stay in the Zoom after the lecture. So we'll start doing that from today. And another announcement is regarding the programming tasks in our homework. So I understand that not every one of you use R for programming. For example, you may use Python. If that's the case, you can use the language you're most familiar with. But for the data set that is in R, like the first data set in the first homework problem, what you can do is that you can load the data in R and then save it as a text file. Then you can load the text file into your Python to start working from there. That's totally okay. And also another comment regarding the t-test, two-sample t-test we talked about last time. I recently read something very interesting online. It's about whether the t-test is applicable when our data do not follow the normal assumption. So when we teach you the t-test, we said, okay, we are assuming a normal distribution so that the t-statistic will follow the t-distribution, right? And let me show this one. Yeah, so this is the t-statistic. However, if your data are not exactly normally distributed, based on the central limit theorem, you will still have the x bar approximately normal distributed and the y bar approximately normal distributed. So central limit theorem can give us this nice result about the sample mean. And then in this case, the question I read in the online discussion is whether we could use t-test to compare two samples that are counts or even binary. So clearly in this case, the data do not follow normal distribution, right? So then what would be your thought on this? So if the data are clearly not normal, but we have central limit theorem, can we still use the t-statistic? So the answer will depend on your sample size. So please be aware that the central limit theorem is for a very large sample size. So that's when this x bar will be approximately normally distributed. But when your sample size is small, then central limit theorem does not seem to be very applicable. However, from that online discussion, I read that there's a very interesting 1987 paper about the robustness of t-test when the data are not normally distributed. So basically, the take-home message is that the t-test is roughly okay if your data do not seem to be heavily skewed, which means that you do not have clear outliers. When you do have that, then you are heavily violating the normal assumption. And then the sample mean, basically, the sample mean as a statistic is not robust to outliers, right? When you change one value to be extremely large, the sample mean will change a lot. So this is the intuition behind why the t-statistic is not very good when your data heavily skewed. But let's say that in a biological experiment, you only have 3 replicates under each condition. So in that case, M1 is 3, M2 is 3. So basically in that case, you have no ways to check whether the normal assumption is reasonable or not. So in that case, I would say maybe t-test is your best bet, given that your sample size is too small. And of course, you cannot afford to do a non-parametric Wilcoxon test or the permutation test. But still, just try to make sure that you think, okay, t-statistic, normal assumption is reasonable for my data. Or if I may want to transform my data by, say, log transformation so that I can apply the t-test more reasonably. Okay, so that's it. And well, let's continue with our discussion. So last time we said that we talk about those tests in the context of frequentist statistics. So in frequentist statistic, what we wrote here is that we assume there's a parameter that's fixed but unknown. We try to construct an estimator from our data. And then we would assume the estimator to be random because our estimator is constructed from random data. If we have another set of data, then the value of our estimator will change. So that's why the estimator is random, the parameter is fixed. And our hope is that the estimator is unbiased. So that means its expectation is equal to the unknown parameter. That means unbiased. And furthermore, we want the estimator to have a small variance. Small variance means that if I redo my sampling for data, the estimator value would not change too much, which means that I get a very stable estimator. So these two properties, unbiasedness and small variance, are what we desire for a good estimator under the frequentist paradigm. Okay, on the other hand, we have the Bayesian paradigm. So in the Bayesian paradigm, the key difference is that you do not assume your parameter to be a fixed value. Rather, you assume the parameter to be taken over possible values. So the parameter itself follows another distribution, which we call it prior. However, given that we have data available, and we assume that the data is coming from a certain parameter value. So given a certain value of mu, we sample our data. Then we want to say what are likely the value of this mu, values of this mu, given we observe our data. So in other words, you try to refine the distribution of the parameter by conditioning on your data equals to the observed data. So in other words, the posterior and the prior are both distributions of unknown parameter mu, but the prior can be thought of as your original belief, and the posterior can be thought of as your revised belief after you see the data. So today we're going to show you that using the Bayesian approach, you can still construct an estimator based on the posterior. Once you get the posterior, you can extract an estimator out of it. And that estimator is usually having smaller variance than the frequentist estimator you may have. And that smaller variance may be something you would desire in your applications because you don't want your estimator to have a too big variance. So we're going to introduce this Bayesian paradigm to you, still in the context of t-test. And we're going to use the estimation of the variance, okay, which is this one. The variance, let me see. So basically we have this one. The sigma square, the t-test assumption, we assume the two samples have the same variance in their distribution. Then how do we estimate the sigma square? So in the t-test, we use the pooled sample variance. That is, we pool the sample variance from sample 1 and sample 2 into one term called SP square. And that is the estimator for sigma square. That's in the frequentist sense. Okay, so let's think of this problem. We still use the same notations. Our sample 1, x1 to xm1, they are IID, normal, mu x, and sigma square. That's my sample 1. And my sample 2 is y1 to ym2, IID, normal, mu y, sigma square. We have those two samples. And we want to estimate the sigma square. That's what we need in the denominator in our t statistic. So how to estimate sigma square? Okay, so the frequentist approach is what we have seen. That is, we use the SP square as we defined. I'm just going to write it again. M1 plus M2 minus 2 times, okay, maybe I would just say, yeah, times, I'll put them together, summation, I from 1 to M1, xi minus x bar squared. That's from my first sample. From my second sample, I from 1 to M2, yi minus y bar squared. Okay, I pull them together into this estimate. And under this normal assumption, we know that this SP squared has a nice chi-square distribution. So we know that based on this definition, we would have M1 plus M2 minus 2 times SP squared divided by the true parameter sigma squared. This term will follow a chi-square distribution with M1 plus M2 minus 2 degree of freedom. This is a mathematical statistics result. And then, because the chi-square is a well-defined distribution, we know its mean or expectation is its degree of freedom, and its variance is 2 times its degree of freedom. So with this in our mind, we could actually write down the mean and the variance for our SP square. So please note that if you have already downloaded the notes, I have updated it. So you could download the updated version on CCLE. So after every lecture, I will try to refine the notes and repost it. So make sure that you can check it back. Okay, so with this, then we have the expectation of this term based on what I just said, equal to M1 plus M2 minus 2. Okay, and then you see that because this is a constant, sigma square is a constant, they can get out my expectation. I would easily show that the expectation of SP square is just sigma square. So this is in our frequentist sense to be unbiased. Now let's look at the variance. The variance of this term okay, by the nature property of the chi-square distribution is 2 times its degree of freedom. Okay, and then you know property about the variance is that once we get the multiplication constant out of the variance, we need to square it. So when I take the M1 plus M2 minus 2 over sigma square outside, I need to square the ratio. So by squaring the ratio, you can show that, and dividing it to the right-hand side, you can show that the variance of SP squared is basically 2 times sigma fourth divided by M1 plus M2 minus 2. So what does this tell you? This tells you that my variance has an inverse relationship with the sample size. M1 is the sample 1 size, M2 is the sample 2 size. So if I have large sample sizes, I will have a smaller variance for my estimator. But if my M1 and M2 are small, let's say 3 plus 3 minus 2, that will give me 4. So if the true sigma square is large, then you can imagine that this variance is large, which means that your estimator is quite unstable. Okay, so when M1 plus M2 is small, then SP squared is an unstable estimator. So being unstable, it means that if I get a different data set, if I redo my experiment for another time, then my SP square value could change a lot. Okay, change a lot for different data sets. So then how do we address this issue? Given that you only have this data set, right? How can you do it? Then the Bayesian idea may be something you can employ to help you. So the intuition Of course, Bayesian has its own philosophy, but here we are using Bayesian to help our estimator construction. So here we use Bayesian by using its flavor that you can combine the prior as your information, as knowledge, in addition to your data. So that hopefully the prior can help you find a more stable estimator. Use prior to construct a more stable estimator. Okay, so before we go into this detail, let me introduce a common technique used in the Bayesian paradigm. That is what we call the conjugate prior. Okay, so maybe it's worthwhile to do a review on the Bayesian and the Bayes theorem, which is the foundation of the Bayesian statistics. Okay, so in the Bayes theorem, let me just use theta to denote the parameter of our interest and use D to denote our data. It's just an abstract symbol. Then the Bayes theorem is simply that the distribution of your parameter given your data is equal to the distribution of data given the parameter times the probability that the parameter take this value divided by the probability of the data or the distribution of data. So if you multiply D to PD to the left-hand side, it's basically conditional times marginal equals another way of conditional times marginal. So both sides are just the joint distribution. That's the Bayes theorem. And because our parameter, we are interested in the parameter, not our data. So if we are concerning that, okay, data being fixed and the parameter is changing, right, can take different values, then this PD can be taken as a constant because it does not involve our parameter, which may change. Okay, so we can write this is proportional to the probability of data given theta or distribution of data given theta times the distribution of theta. So here it depends on whether we are in the talk about discrete random variables or continuous random variables. So there's a little difference there. For discrete random variables, here we are talking about the probability masses, or the probability mass function, such as the probability of a Bernoulli variable taking value 1, that's what we call P, right? But if theta is continuous random variable, here the P means density, probability densities. So for the distinction between a probability mass or probability over and the probability density, I will defer you to some background reading. So if that's something new to you, please check it out to make sure that you understand it. You can search it for what's the distinction between probability and probability density. Okay, so for now, we are not going to distinguish those two. And then you see, this is the result we use in Bayesian statistics, which is very interesting. We call this the distribution of parameter given data, the posterior. And we call this the distribution of data given parameter, the density, or it is the likelihood. So when we write it as likelihood, we often write it as L theta. Okay, we often write it as L theta given our data. You can put data here or you can choose to leave it out. Either way is okay. But this L means it's a likelihood function. So when we write it as with the argument at theta, we mean that the likelihood is a function of theta. It is equal in the form to the probability density of data given theta. But I just want to make sure that you know the slight difference. So when it's written as a density, the argument are the data points. While when you write it as a likelihood, the argument is the parameter. So there are two functions defined on different spaces, but they take the same form. It's just which one you treat as fixed. Theta as fixed here, or the theta as fixed here. Okay, and the third term is what we call prior. So in Bayesian statistics, you see, by this formula, you can clearly have the posterior as a combination of likelihood and prior. Okay, but the key question is, how do we specify our prior? So if you are truly Bayesian, in the truly Bayesian problem, the prior is an actual prior. That is your knowledge. For example, coming back to our example here, the prior may be, you know how the value of sigma square are distributed. For example, you can assume, say, okay, I know it's about 1, right? It's slightly deviated from 1, then I can probably assume a prior on sigma square with a large probability density on 1 with some small standard deviation. That's something you could assume. But in reality, in most cases, we don't have an actual prior. And this is where the controversy arose between frequentist and Bayesian. And people in those two paradigms have been fighting with each other for many, many years because of this controversy. So they said, okay, the frequentist people say, you think you have a prior, but you don't. Then your prior is a fake prior. But the Bayesian people would argue it against with frequentist by saying that, okay, you assume sigma squared to be a fixed constant, but in reality, it could take different values. So anyway, so we are trying to put that aside, but just to see what can we do in practice if you don't have a prior. How would you suggest a prior or find a prior? So this is an important concept you will see in a lot of bioinformatics method papers. This is called conjugate prior. So conjugate prior is a prior class such that it makes the posterior and the prior itself in the same distribution family. So for example, if you assume the prior follows a beta distribution, then if you follow the Bayes rule, you have the, let's say, the likelihood, which is given how you assume the data is distributed given the parameter. Let's say this is binomial or Bernoulli, and this is beta prior. Then multiplying them together, you see that for the posterior, which is still a distribution of theta given d, it's a distribution of theta. If it's still beta, then we can say beta is a conjugate prior of binomial. So let's look at that example to help you understand it better. So let's say that we assume our data and data points x1 to xn, they are IID from a binomial distribution with total n and the positive probability p. So this is our data generation model, right? We assume the data come from this, and the p is our parameter of interest. So given this, we can write down the likelihood of p as the joint density of my data. Okay, given p. And we know the formula for binomial because they're IID and can multiply their probability together. So for each xi, the binomial probability is n choose xi times p to the power xi times 1 minus p to the power n minus xi. Okay, that's the probability for each xi. And I multiply them together because of the IID. Okay, then you can see that this term, if I simplify a little bit, it becomes n choose xi. I leave it out. Oh, sorry, I should say I put a product here. I from 1 to m, n choose xi. And then I can put this product into the exponent for this term and this term. I can have a p to the power summation xi times 1 minus p to the power, what will be here? It will be n squared minus summation xi. That's my likelihood for p. And then my goal is to find the prior such that when I multiply the prior with this likelihood, the resulting posterior will be in the same family as the prior. Then I need to identify what prior is this. So basically for the prior, I would need its probability density, because P here, clearly P is continuous. P can take value between 0 and 1. Probably I should put 0 here. Yeah, between 0 and 1. Then it's a continuous value. So P as a prior, it should follow a continuous prior distribution. So let's look at the distribution form we may use. So to have the product still similar to this one, we need to have the prior in the form of P to the power of something times 1 minus P to the power of something. And so for this case, if we are familiar with the common distributions, so you can usually look them up, the density functions for some common distribution, you would immediately recognize that this should be the beta distribution. Okay, so if we assume the prior to be beta, beta needs two parameters. Let me call it alpha, beta. So, and both of them must be positive. So now let's assume that alpha and beta are known, or we specify them. Then the prior distribution for P, it will have this form. So this is some gamma function, alpha plus beta. So I'll make a correction to the note. I noticed that there's a typo there. The gamma, which is a Greek letter, was written by mistake as capital T, but it should be gamma. So it's a gamma math function that you can ignore it for now. But this is the constant, and it times the p to the power alpha minus 1 times 1 minus p to the power beta minus 1. So these are the two key terms because they involve the parameter p. So then you see the posterior as a combination of the prior and the likelihood. We can write it as p given my x1 to xn, given my data. This will be proportional to this multiplied by this, and I will drop all the constants that do not involve p. Then clearly you see I would have power summation xi plus alpha minus 1 times 1 minus p to the power n squared minus xi plus beta minus 1, right? So this will be the two new powers in the posterior. And based on that, this prior, this density corresponds to beta, alpha, beta, right? Alpha is just the power of p plus 1. The beta is the power of 1 minus p plus 1. Then we can immediately recognize that the posterior is still following a beta distribution. And the two parameters now become summation xi plus alpha and summation, n squared minus summation xi plus beta. So we can immediately recognize that. That's the posterior. So you see here, the posterior is still a beta distribution, just as the prior. That's why we say the beta prior is a conjugate prior to binomial distribution. So in other words, conjugate prior is defined based
Professor,
on
I have a question. Why is it n squared again?
The reason is that when you have this product multiply here, you need to take the summation for n minus x1 plus n minus x2 plus n minus xn, right? So n appear for n times, that becomes n squared. Does that make sense?
Yes, it is. Thank you.
Okay. Okay, so yeah, so this is just an example to show you what is a conjugate prior. Okay, but the question I left here is that this posterior is not directly usable yet. So usually we would find we will construct an estimator from the posterior by taking either the expectation of the posterior or the mode of the posterior distribution. Okay, so what I mean is that, let's say if you have, this is the posterior distribution, theta given d, that takes this. And if you pick this value and call it an estimator, theta hat, so you will pick this value to estimate theta. This makes sense because this is the value that you think theta is most likely to take given the posterior distribution you calculate. And because we're maximizing the posterior to find the theta hat, we call it MAP, maximum a posteriori, short as MAP. So this is one way to compress a posterior distribution into an estimator. Another way is to take the expectation of the posterior. So this is what we call the Bayes estimator. So Bayes estimator is by taking expectation of this distribution, theta given d. If this distribution happens to be symmetric about its mode, then those two estimators would coincide. It will be the same one. But in many cases, they're not. Okay, so coming back here, if we are going to use the Bayes estimator to estimate P, okay, so then the P hat Bayes, it will basically be the expectation of this beta distribution. And we know the beta distribution's expectation is just determined by its two parameters. It's the first parameter divided by the sum of the two parameters. So in other words, I can easily write it as summation xi plus alpha divided by their sum. So it's n squared plus alpha plus beta. Okay, that will be the Bayes estimator. But if you compare it with this original data distribution, okay, if I just do the maximum likelihood estimation, then I can easily show that by doing maximum likelihood estimation. I didn't talk about it, but it's basically you try to find the value p to maximize this likelihood function of p. And this is something the 100B class covered, right? The estimate, so what you will do often is to take the log, to change it to a log likelihood, then this power will go down, and then you do the derivative of the log likelihood, set that derivative to 0, solve for the p-value, and that's the MLE, maximum likelihood estimation. So here, I'm not going to do the derivation, but we can show that MLE is actually of this form. So just the summation of xi over n squared. So you see, comparing the Bayes estimator to the MLE, you see they differ in that the Bayes estimator has a constant alpha to be added to the numerator, has constants alpha and beta to be added to the denominator. And we know that in the prior, okay, in the prior, if we just look at the prior, its expectation is alpha over alpha plus beta. That's the mean of P with the prior only. And this MLE is based on the data only. And this Bayes estimator combines both. It's basically a weighted average. So you can expand it as a weighted average of the MLE and the prior mean. So that's why we say that the Bayes estimator is a combination of information. And we can show that compared with the MLE, the Bayes estimator will have a smaller variance. That's what we desire. But there's always some trade-off, right? You achieve a smaller variance, but what you lose is the unbiasedness property. So the Bayes parameter is biased because it's biased towards its prior, the prior specified. Okay, do we have any questions about this? This is the whole idea of using Bayesian framework to construct estimator. Okay, so one thing I didn't talk about yet is how do we specify alpha and beta? These are the parameters in my prior. So for now, I said that we just arbitrarily set alpha and beta to be some values we think are reasonable. But still in practice, even though you specify the form of the prior to be beta, alpha and beta may not be directly available or difficult to obtain. So how do we do that? So here comes the idea. It is called Empirical Bayes. You might have seen it in some papers which say, okay, we use the Empirical Bayes approach, but you may not know what it's exactly about. Here, let me just make it simpler for you. So Empirical Bayes means that you use data, in this specific example, x1 to xn, to estimate alpha and beta. So in other words, the prior parameters alpha and beta also come from your data. That's where the empirical stands for. So in statistics, when we say something empirical, we mean that it's based on data. Okay, so how do we do it? So the idea is still to use data to maximize some likelihood about the prior parameters. Okay, so let's take a look. So now you see that we have this, so I should say, think about this. Okay, so coming back to the Bayes theorem. So if we write it out in more detail, you would have this. So the prior now depends on alpha beta. So I'm going to write it as P given alpha beta, right? When you write down the prior, you're doing this. And for the likelihood, LP given x1 to xn, right? We can say that it's taking the same form as the joint density of x1 to xn given P. That's it. And in the Bayes formula, to get the posterior, we will multiply the prior with the likelihood. And what will we get? So multiplication will give us this joint density, which is x1 to xn and P, okay, given alpha and beta. And what can I do to get rid of the P so that I'm only left with my data and the parameters, the prior parameters I want to estimate? This is the empirical Bayes. So the goal is that you want to remove P because the P can take any value here. It could take any value between 0 and 1 for the special case, right? And it will not help us estimate alpha and beta. So to estimate the prior parameter, the rationale is that we want to integrate out P by considering its all possibilities. So here P can take values from 0 to 1. And then I want to say, okay, on average of the P, what are the values of X, alpha and beta, so that given this value of alpha and beta, I am most likely to observe my data regardless of P. Okay, so let me write it down for your information. So if we integration, what we do is that we can have just the joint density of my data given alpha and beta. P is no longer there by doing integration. Okay, and P is from 0 to 1. I'm doing this integration. And this is what a common technique used in probability. That is, we start from joint density, But if we're only interested in the marginal density of one set of variables, but not the others, we would just do integration to integrate out the other variables by over its range. Here, the range is from 0 to 1. Okay, so suppose that we can do this. And in fact, yes, we do. So in this example, you see that this joint density is to multiply this prior, okay? Sorry, my bad. Is to multiply this likelihood right here, the data distribution, with the prior. Multiply those two, and you can see that the function is like the posterior function, p to the power of something, 1 minus p to the power of something. And then you're going to do the integration of this. So after the integration, you are left with x's, right? They are still here. After do the integration, the x's will stay here, alpha will stay here, beta will stay here. So you will get a function of with x, alpha, and beta, but no longer p. And we know that we can do this integration for sure, because we know in the beta density, any density can be integrated to 1, right? So this is the role of this constant plane. So if you just integrate the second part right here, you know the integral result would just be the inverse of this constant right here. Okay, so similarly, I'm going to leave out the detail, but just for your information, we can get the result, and this result will be a function with just alpha, beta, and the data. So we can think of this as a likelihood of alpha and beta given our data. Then the next step of empirical Bayes is to find the value of alpha and beta to maximize this likelihood, okay? The likelihood of this prior parameters. So what we do is that we try to find, we call this alpha hat, beta hat, by maximizing this L, alpha, beta, given my data. So we often use this argmax notation. The argmax means that the value of alpha and beta that maximize this function. And we return those maximizer as alpha and beta. Okay, so then with this, we will use those two estimates by maximizing the likelihood as our prior parameter. Okay, so coming back to this, so then use alpha and beta hat in either you want to use the Bayes estimator or you want to use the map estimator. Either one is okay, up to your choice. But that's the whole idea of the empirical Bayes. So if we want to use the Bayes estimator, then this estimator becomes something achievable solely based on your data. So it's summation of xi plus alpha hat divided by n squared plus alpha hat plus beta hat. Okay, so there is some controversy regarding empirical Bayes, just for your information. Just as I said, the frequentists, the hardcore frequentist people are against the use of empirical Bayes because they think the prior is not the real prior. It's just something you made up, and then you try to use the Bayesian framework. But on the other hand, you can think of empirical Bayes just as a tool for you to get an estimator that's slightly different from the MLE estimator, right? So you basically, by putting additional assumption that the prior is of the beta shape, beta family, but I don't know the beta parameters alpha and beta. So I use my data again to get the values I think are likely for the beta parameters. Then I use my estimates to construct this new estimator. But still, X is my data, alpha hat, beta hat, they're both from my data. So this is the idea of empirical Bayes and the Bayesian framework to get a Bayes estimator. Do we have questions?
I have a question. So I don't know exactly how to say this, but it feels like there's something kind of circular about empirical Bayes, if that makes sense. Like, maybe that's more of like a comment. I'm not really sure what I'm asking, but like, it just like, does that make sense?
So I think your argument is just why the frequentist people think philosophically is you are basically contradicting yourself by using data to learn the prior. I think that's your point, right? Yeah, but if you don't like the Bayesian idea, you can always think of Bayesian as a hierarchical probabilistic model. You can think of this is the first layer of probability, that's the distribution of P. And the second layer of probability is the distribution of data given P. Then given those two-layer probability model, you have parameters including the first layers alpha, beta, and the second layer, which is the P, right? Given alpha, beta, you draw P, and given P, you draw your data. So then the goal is to estimate the P, which is the intermediate parameter. So then the empirical Bayes idea is that I first use MLE to estimate the root level parameters alpha and beta doing MLE. And while doing that, I integrate out P because P is just the intermediate parameter. And then with alpha and beta, I use the Bayesian idea to get a Bayes estimator for P, which is like this. But here the parameters are what I plug in from this MLE. Yeah. So I would say it's just a way to construct an estimator. And people have shown that if you use the frequentist framework to evaluate this estimator, you can show that it has smaller variance than the MLE estimator for P. And although it's biased, right, but still there's a trade-off, which is what we call the mean squared error. Let me put it here. So mean squared error, or MSE, is a criterion that frequentist people use to evaluate an estimator. It's defined as the expected squared difference between P hat and P. Okay, so for this term, this is how you want to say whether an estimator is good or not. And interestingly, we can actually decompose it into two terms. The first term is this, expectation of P hat minus P squared plus the expectation of P hat minus its own expectation squared. So this is what we call the bias mean trade-off. You can see this is the bias of P hat squared, and this is essentially the definition of variance of P hat. Okay, so if the MSE is your criterion, then it's very likely that an estimator may have bias, but given its reduction in variance, then overall its MSE is better than an unbiased estimator. Okay, so the MSE and the bias is talking about two different things. MSE is okay, overall, what would you expect to be the squared difference between your estimator and the true parameter, right? This is something you want to minimize. But bias is one side, variance is another side. Okay, thank you for the question. Yeah, so if you want to talk more about the frequentist and Bayesian, if you're interested, you can check online. There are a lot of discussion and debate over the years, maybe in the past century. Okay, so then let's use what we have learned just now to revisit the problem. To revisit this problem, how can we construct a more stable estimator for the sigma square? Okay, so we already have this data distribution already. So let's come back to the estimation of sigma square in this case. We already have the distribution of SP square given sigma square, right? We know this already. This is from our data. And this is the parameter of our interest. Parameter. We know this from that chi-square property from here. So given this distribution, it's essentially the distribution of SP squared given sigma squared. So I'm going to define this as the D. For my notation simplicity, I will call M1 plus M2 minus 2 as my D. Okay, so then what I already have is that D times SP squared over sigma squared follows chi-squared with D degree of freedom. I have this already. Oh, this is my likelihood part. Likelihood is how the data is distributed given a parameter. Now further, prior, right? So if we want to use the conjugate prior idea, we need to write down this likelihood so we can see what can be used as a conjugate prior. So I'm going to do that. And so basically this tells me that, okay, the density of SP squared given sigma squared following the chi-square density, I can show that it is proportional to, because this is the random variable that follows chi-square. So this is D times SP squared over sigma squared to the power of D over 2 minus 1. So this is chi-square density, and another term is exponential term, exponential to the power negative D SP squared sigma squared. So you see our sigma square appear in two places. One is here, one is in the exponent. Then we need to find a prior distribution. It will be a distribution for sigma square, and we needed to have a similar form. That is sigma square to some power and sigma square in the denominator of an exponential term. Okay, and luckily, we have a distribution for that. It's called the inverse gamma distribution. Okay, so this will give us conjugate prior of sigma squared. So we call that inverse chi-square distribution. And it's a special case of the inverse gamma distribution because chi-square is a special case of gamma distribution. For those, you can check out the Wikipedia page to see what the distribution is like. And this inverse gamma distribution takes two parameters. We call, here we just denote them as nu and as 0. Okay, so in detail, if we assume this conjugate prior, the prior density would be proportional to. So here we are just trying to be simple. We ignore all the constants that do not involve the parameter. Then this prior density would be sigma squared to the power 1 minus d over 2 times exponential of negative d times SP, let me see. Sorry, my bad. No, oh, my bad. Sorry. This is right. The prior is sigma squared to the power negative nu over 2 minus 1, right? And the second is exponential to the power negative nu S0 squared divided by 2 sigma squared. Okay. So you see that here I have the same form, sigma squared to some power, just like here, right? Because here you see, if I further just keep the term of sigma squared, it will be sigma squared to the power negative d, or sigma squared to the power negative d minus d over 2 plus 1. So that term can be combined with this term when I multiply them. And the second term are exponential, and sigma square is in the denominator here. So I can combine them. So just by doing so, you can see that I can have the posterior, which is P of sigma square given as P square. This will be proportional I'll do algebra and simplification of sigma squared here to the power of nu plus d minus 2 over 2 minus 1. Okay, I want to keep this form, something minus 1. Then I can immediately recognize, okay, the first parameter of inverse gamma is this mu. So I want to create this nu. You see that in the posterior, by creating this form, the numerator here will be the first parameter of the inverse gamma that corresponds to the posterior. And the second exponential term, by simplification, I can obtain it as 2 sigma squared negative nu S0 squared minus d SP squared. Okay, so now you can recognize by comparing this posterior form, clearly it's in the same family as the prior, both inverse gamma. You want to recognize then what is the first parameter and what is the second parameter of this new inverse gamma. So clearly the first parameter, I get it here, right? It's nu plus d minus 2. That's the first parameter. And from here, from the prior, I know the numerator in the exponential term, ignoring the negative sign, the numerator is just the product of the first, sorry, I missed the square. It's just the product of the first parameter and the second parameter. So if I see that, I can clearly show, okay, this, we move the negative sign outside also. We will show that here, this is the product of the first parameter and the second parameter. So then the second parameter is clearly nu plus d minus 2. And the other thing is nu S0 squared plus d SP squared. Okay, so now I can easily derive what's the corresponding parameters for the inverse gamma for the posterior. The reason I want to do this is because then I can easily get the expectation of this inverse chi-square based on what I know about the special distribution, because we have derived its expectation already. Okay, so then I can get the Bayes estimator. Now I'm assuming the nu and S squared to be known, so I'm not touching that part yet. Let me see, do we have a question in the chat box? Did you miss factor 2 in posterior exponential term? No, I don't. So you see that here, oh yeah, I think, and I see what you mean. Yeah, I think I missed one here, correct, yeah. Thank you for the correction. Yeah, in the likelihood part, I missed a factor 2 in the denominator here. Otherwise, it doesn't add up. Thank you. Okay, so now let's see. So for this Bayes estimator, I'm going to take the expectation for the posterior. Okay, and it's a very interesting fact that this is just equal to the second term. The second parameter is just its expectation. So here the prior's expectation is, I forgot to say that, is just as 0 squared. That's just how the distribution is defined. Okay, so then in the Bayes estimator case, okay, so in the Bayes estimator case, we have it as nu S0 squared plus d SP squared plus nu plus d minus 2. And now you can see why it is a weighted sum of prior and our data. So this prior means, okay, this is what we believe the sigma square is going to take on average, our prior belief, S0 squared. And SP squared is what we compute from data. And if in the case that when just nu plus d is much larger than 2. When that happens, we can just ignore this 2. Okay, it's approximately nu plus d mu s0 squared plus dsp squared. Okay, and then you can see how it is a weighted sum. It's basically nu plus nu over nu plus d times the prior value we believe plus d over nu plus d times the estimator from data we have. So we are basically finding a trade-off as our new estimator. And the trade-off lies between the prior value we believe in and the estimated value from our data. Okay,
Professor,
so that's the estimator.
Professor, I've got a question. Can you explain a little bit more why?
So for those of you who ask questions, can you turn on your camera so I can know who is asking the question?
Yeah, I'm actually.
Okay, hi. Okay.
Yeah, I'm just. Can you explain a little bit why expectation of sigma squared is S0 squared? Is that the property of the scale?
That's just the property of this distribution. It's basically how you define the parameter. So basically, when we say the parameter is nu and S0 squared, this is what we mean here. But this may be a little different from the Wikipedia page. In the Wikipedia,
That's why I was confused, because the Wikipedia page is a little different.
Yeah, especially if you check even the gamma distribution, if you check the Wikipedia, there are 2 sets of parameterization. So one is using a rate and one is using another name I forgot, but it's just 2 ways of parameterize the same distribution, but there's one-to-one map between those 2 parameterization, but they're actually the same thing. So here we just use this parameterization for our convenience.
Okay, thank you.
Yeah, thank you. Okay. So that's the Bayes estimator. And then we talk about empirical Bayes, right? If the nu and s squared is something you don't know how to specify, then you can do it. You can use that empirical Bayes to find the nu and s0 squared to place it back. Then you will have this Bayes estimator. Or in some cases, I think you do in some cases, you may have prior learned from external data. So for example, I can give you a context for applying this Bayesian framework. Let's imagine that in a single cell data analysis, single cell gene expression data analysis, you have some parameter you want to estimate, but one issue with single cell data is that it's super sparse. You don't have many reads mapped to each cell. In other words, the data information per cell is quite limited. So in that case, if you want to borrow some information from bulk RNA-seq about this gene in public database, then it's reasonable that you construct a prior based on those existing data about this gene. And then you combine that prior to your single cell data to get an estimator. So that's one possibility. And you can check that if single cell is something you're interested in, and for example, the project data is about single cell data, right? You can check that in the literature, there are indeed several papers already that use the Bayesian idea to estimate gene expression parameters. Okay, so I guess I can stop here. And for this part, for the empirical Bayes part, and for this Bayesian estimator part. So hopefully it's not too intimidating. But if this is the first time you hear it, probably there are a lot of things you need to take a closer look and think about by rewatching this video probably. And then you'll see, okay, that's making more sense to you. And also, just to be sure that this Bayesian framework are all under probability models. So you must assume your data come from a probability distribution to be able to use this Bayesian framework. This is something to keep in mind. Okay, so our next topic is regarding data normalization. It's a very practical thing that we must do before we do any differential gene expression analysis. Okay, so normalization. But I have to acknowledge in the first place that normalization is a very controversial topic. When different people talk about normalization, they may actually mean different things. So please make sure that you understand what this normalization is actually about. But intuitively, normalization is to make sure that data in different batches or in different biological samples, right? I specifically say biological samples because in the second class, we said that the statistical sample is different from what a biological sample is. In a biological sample, we call the genes, thousands of genes measured in one tissue as a sample. But a statistical sample, we consider IID observations as one sample, so that they're basically orthogonal. So we want to make data in different batches or different biological samples comparable. So this is the key. What do you think as comparable? Okay, so in RNA-seq data, let's use that as an example. So in RNA-seq data, a very important, or I should say bulk RNA-seq data. This is specific to bulk RNA-seq data, which we mean measured by tissue. And each sample is sequenced separately. Okay, samples sequenced. Biological samples sequenced separately with different, maybe different sequencing depth. So in the sequencing data, sequencing depth is the total number of mapped reads. After you do the read mapping, how many reads are mapped to genes, right? So the first and most usual way is to normalize by sequencing depth, or sequencing depth is sometimes called library size. These two terms are both used for the sequencing literature. Right, why do we want to do that? Because the number of reads, let's say I call this, okay, let me call this, is the number of reads mapped to gene I in sample J. Because the deeper you sequence, the larger the Xij. There's a linear relationship between that, right? So we don't, and the number of reads do not really capture the number of molecules in our biological system. The reason is because we have the PCR amplification, and the number of sequencing, right? The PCR amplification will amplify each molecule into multiple copies, and you're sequencing the copies. And the sequencing depth will determine how saturated your sequencing library is sequenced. If your depth is very deep, then every molecule in your sequencing library, that means after PCR, you load the library to the sequencing machine. Then hopefully every molecule in the library will be sequenced. But if your sequencing depth is low, then many molecules will be missed by the sequencing machine and not sequenced. So therefore, you can roughly think there's a linear relationship between sequencing depth and the number of reads you obtain mapped to gene I in sample J. So it makes sense to do the normalization. And there are two common approaches for doing the normalization. So one, you can see this in the literature. One is called RPKM. That stands for reads per kilobase per millions of reads mapped. Okay, so I'll just write it here. Reads per kilobase per million of mapped reads. So the second one is to divide by the sequencing library. So what would you do? So the first thing is that by doing the per kilobase means that you want to standardize the gene length. Because imagine if you have a gene with 1 kilobase versus another gene with 3 kilobase, then if both genes have the same expression level, you should have more reads in the second gene, the longer gene, right? You'll capture more reads. So that's why we want to normalize by the gene length. And we also want to normalize by the sequencing depth. So here, let's say RPKMIJ. Okay, it's defined based on Xij, that's the number of reads, divided by the length of gene I. Okay, I'll call this Li as the length of gene I in KB. And furthermore, by the total number of reads divided by 1 million. So here you are going to take the summation over I. Maybe I call it I prime, X I prime J. So you take the sum over all the genes in sample J, and you divide the sum by 10 to the 6th. That corresponds to 1 million. So if you do that, you can convert the read count into an RPKM. But then later, people started to question this criteria because they think, okay, it's not reasonable to normalize the sequencing depth by the number of reads, but you should normalize by the number of molecules. What's the difference? So let's say that if you have a gene, let's say 1 kb, and you have a gene 2 kb. So let's say that you have the same number of molecules. If you have the same number of molecules, because the reads are just fragments of the cDNA molecules, and the cDNAs are reversely transcribed from the messenger RNA for RNA-seq. So if they have the same number of cDNA molecules, you would have twice more the number of reads in the long gene, right? The number of reads here should be twice of that. So therefore, if you're doing normalization for the number of reads instead of number of molecules, you are basically not treating those two genes in a fair way. So then later, people proposed this so-called TPM. It's just called transcript per million of mapped reads. So what does it mean? It means that in the denominator, your sequencing depth is not defined by the total number of reads in sample J, but the total number of molecules in sample J. And you are trying to approximate the number of molecules in gene I based on Xij divided by Li. So therefore, here the TPM is defined as the TPMIJ is defined as still the numerator is Xij divided by Li. That's the approximate number of molecules of gene I in sample J. But the denominator is different. It's actually the summation of I prime Xi prime J divided by Li prime. For every gene, you normalize its read count by length first before you take the sum over genes, and then you divide this by 10 to the 6th million. Yeah, so basically, this is the TPM. And you see that their rationale, the difference between their rationale is what you think should be the normalization factor. And I saw that Kimberly has posted a blog by our faculty member, Harold Pimento here, who joined UCLA very recently, and it's about this discussion. Yeah, thank you, Kimberly. So if you compare those two things, you will see that it's just how you believe the sequencing depth. That's different. Okay, I see. Albert, you're rotating there. Okay, so that's the TPM and that's the RPKM. And a related concept, as Kimberly just posted, is the FPKM. So FPKM and RPKM, I would say they are very similar to each other. The slight difference is that FPKM deals with paired end reads, while RPKM was a concept that was proposed when we only have single end reads. So by paired end reads and single end reads, the difference is that given a fragment, okay, let me explain a little bit. A paired end read means that you sequence both end and you retain them as a pair. While in single end read sequencing technology, you only retain them as individual reads. You lose the pair information. So in other words, in single end data, you count reads, while in paired end data, you count pairs. So each pair is called a fragment. So that's why this FPKM, the F stands for fragments, blah, blah, blah. So that's the slight difference. And using paired end data in your analysis, if you want to count fragments, then for the reads that loses its pair, it will not be counted. It will just be discarded. Okay, so I guess we can stop here. We just give you a very short, brief introduction to the simplest way of RNA-seq normalization. So now you're aware that the FPKM and the TPM units are already supposed to be normalized. And also, I can post another paper regarding the discussion of RPKM and TPM to our CCLE. That can be used as a supplement to the blog Kim just posted. Okay, so I'll stop the recording here. And for